Hello everybody. Hi there. I'm just going to go through an unbalanced delta and we'll look at the vectors, the voltages and how we apply that to the apparent power and work out the real and reactive power. And as I say, it's unbalanced. I'm going to use the same values of impedance as I did in the star example, and it's going to illustrate something about the difference between a delta and a star in terms of apparent power and power consumption. Right, so I'm still having a bit of trouble with the light on this, although it's not too bad just now. And that's from the other day, yesterday. Right, I'm going to do them on the board and then do them on that as well, just to show if anybody can't quite see anything. Right, right, so let's work out I current going through AB. That is going to equal VAB over ZAB. You see that, right? And so that's 415 at 0 degrees divided by ZAB was 50 at 30 degrees. 50 at 30 degrees. Yeah, and that is going to work out at 415 divided by 50. That's 8.3 amps at minus 30 degrees. You see that? So that's the first one. Then, so we've used this one VAB, right, for that. So let's just write that up there. IAB equals 8.3 at minus 30 degrees. So let's find out IBC. You see that? Equals 415. And we're using the minus 120 degrees from here. And that was 100 ohms at 50 degrees there, which equals, that'll be 4.15 looks of it. Remember, so that's minus 120 minus 50, so that's going to be minus 170 degrees. Right, amps. So we'll put this up here. IBC is equal to 4.15 at an angle of minus 170 amps. That's this one. And now ICA equals 415 at 120 degrees. That's this one. Divided by 75 at minus 20 degrees. Yep. this is equal to just a quick look at that again, written down here. VAB, VBC and VCA with associated impedances. You get your line to line. You find that the line to line current has a 30-degree offset from your initial line 1, 2 and 3 here. And what we do is we want to use this as a reference voltage here, so we rotate that around 30 degrees and add the 30 degrees to all the other vectors, and that means we're left with VAB, VBC and VCA, and we can kind of disregard these. We don't really need to know what these are. Right, so that works out 5.53. 5.53, an angle here of 120 minus, which is plus, so it'll be 140 degrees. Yep. So that's is that recording? ICA equals 5.33 at an angle of plus 140. Right, so I really hope you can see that. So what's going to happen here then, if we look at the vector diagram, V, A, B, V, B, C, V, C, A. Right. This IAB is at minus 30. From AB. IBC is minus 170, so that was 120, so 50 degrees, maybe something like that, maybe not quite, and it'll be smaller. Small, but I'm not really drawing these to scale, I'm just trying to get the kind of angles, right? And that's 120 to there, minus 120, but another 50, minus 170 altogether, but it's going to be minus 50 from VBC. In other words, these are inductive and the current is lagging. Remember civil. And with this one though, we've got 140, remember this is 120 degrees, this current's up here somewhere, and that's plus 20, and that makes that the 140 altogether. But the voltage is at 120, so relative to CA, the current CA, voltage CA, the current is leading it, which would happen in a capacitor, or a capacitive, or a device with capacitance. So we'll just mark them in, so that's VAB and IAB, VBC, IBC, VCA, ICA. And then when we go to do the power calculations, remember what I was saying in the last video about using the conjugate? Because the conjugate tells you the difference just between the two vectors you're looking at, rather than right round to the reference point. And so that means when you use a conjugate, it does just tell you whether it's leading or lagging, and the difference that is. And again, that helps you map it onto that quadrant and other quadrant if it's capacitive. Now, so I hope that's making sense. I know it's quite hard to visualise what's going on at times. Now, I will look at the currents now, and so I'm going to stop this now and do a wee. Again, just to quickly show you, if you couldn't see on the board there, I've worked out the currents, VAB over ZAB, VBC over ZBC, and VCA over ZCA. And there you go, there's your phasors there. And what I've done here is I've drawn in the voltages, VAB, and the associated currents for each line to line. And the currents on pen there. And that's just to illustrate again that IAB is lagging by 30, IBC is lagging by 50, but ICA is leading by 20. So, and what we do now then is when we work out apparent power, we need to work out just like we do in the single phase and the star. Actually, we just do exactly the same. But we'll get to that in a wee second. I'm going to go back to the board. Right, if we consider this wee setup here, L2 and L3. So we could call that, I suppose, this. What we're going to look at, we're going to look at what would happen if we put an ammeter on each one of these lines here. We're going to find out what the line currents are going to be for that I1, I3 and I2. So if, say, you get unbalanced situations, see like a block of flats or something like that, you would have a single phase input to each. Say it was a block of 3, you would have a single phase, but that would be coming from a 3-phase supply. You can imagine each flat wouldn't have the same amount of machines on at the same time, or whatever, say different power consumption. That's where you get unbalanced. Just an example of an unbalanced kind of setup, anyway, just in case anyone was wondering. Now, what we're going to do is work out these currents. We've worked out IAB, IBC and ICA there. Now, if we look at this and we want to work, say we wanted to find out what we reckon is going to go through this ammeter here, and that's going to be I1. What we've got there then, and if we look at it, say we say to ourselves the current is moving from left to right. So for instance here, this I1, it's got IAB is coming up this way, but looking, and we have to apply Kirchhoff's law here, Kirchhoff's current laws. We will look at each node individually, and this node here, you would have IAB going from left to right, and at this point you've got ICE coming in this way in the opposite direction, so that's going to get subtracted from that. Looking at I2 here, at this point we would have IBC travelling that way minus IAB, so that's IBC minus IAB, and at this node here we're going to have ICA minus IBC. And that's how you work out each line current that you're drawing. So each flat and this kind of thing would be drawing a different amount of current down each line, and if they were all balanced, it would be the same amount of current getting drawn in each line. So I hope that's making sense. So the direction of current flow is like that way, and this one kind of goes like that. Hope you can see that. Now, what I'm going to do now then is we'll look at the power and hopefully it will tally up with what we did in the star, actually, because there's a connection between star and deltas. Just make sure that's recording. So what we're doing, we've got the current and we've got the, so if we want to find out for AB, the apparent power for AB is going to be voltage AB times the current AB conjugate. So that's going to be 415 at 0 degrees times 8.3 at 30 degrees. What's that? 415 times 8.3, that's 3,444. 3,444.5 volt amps at 30 degrees. Good stuff, that's the first one. So what I'll do is I'll just put this up here. Well, what I'll do here maybe. That's what I'll do. I'll put them on this wee bit of paper down here. So S A B is equal to 3,444.5 volt amps at 30 degrees. Excellent. So I'll rub this out. Now SBC is 415 at minus 170. No, in fact, oh sorry, that's the current. This should be minus 120 actually. Minus 120 is the angle times the conjugate of this one here. Sorry, that is wrong. Sorry, that's what made me mixed up, because I seen the 415 there. Because it's 415 volts times 4.15 amps at minus 170. Well, it's plus 170 here. Yeah, that's minus 120 there. So SBC, that's voltage BC, which is 415 at minus 20, and this is IBC conjugate. So that minus 170 goes to plus 70, and that's going to give us 415 times 4.15, 1722.25. An angle of minus 20 plus 170, 50 degrees. The beauty of the conjugate. Right, so I'll write that down here. Oops. SBC equals 1722.25 at an angle of 50 degrees. And this last one, SCA is going to equal VCA times current CA conjugate, which is, what was that, 415 at plus 120 times that 5.33 an angle of minus 140. The conjugate again. Sorry this is bending over, I've not really got a lot of room here. It's a bit awkward, unfortunately. But anyway, goodies never say die, so who cares? Right, and so that gives us, that'll give us 415 times 5.33, which is 2211.95 amps. I'll write that down here. Don't worry, it'll be straight on the bit of paper there. So SCA equals 2211.95, an angle of, that'll be plus 20, no, that'll be minus 20, yeah, because that's capacitive. Right, so I can rub that out. And then you have to go through that blooming process. Sine, cos, cosine. Turn them into rectangular. It's time consuming. But don't worry, we'll get there. So SAB, so I'll do it up here, but I will write it down. Equals cos, S cos AB cos theta plus SAB sine theta, and that's your real power and that's your reactive power. So what's that? And once we work these out, we just add them together, just like we did with the star. So that's 3444.5 times cos of 30. That's 2983. I'm going to just take all the wee decimals out, can't board them. I don't know if this will be plus, that'll be plus obviously. So you think about it, that's kind of like your I, and this is your J part. And what was that? 3444.5 times the sine of 30. 1722. Right, just leave it at that. That's your J. Obviously, but that is your R and that's your Q. You know, that's your R and your Q part of your triangle, and that's your S. Remember that? Hope so. We've done it many times. So that's your real, and that's your Q for that one. So it's then SBC was 1772. So we'll just quickly do that. That was 50 degrees. That's on this 1107 I plus that's 1319 J, and SCA is going to be That's 2079 I plus and that's going to be minus 757 J. That's minus, it's capacitive. So I'll write all these down here again as well. That's going to be 298. I'll just put this on. Right, and when you add all these up, what we've got there, there's 6169, your power, and your reactive power 2284 up the side there. We just use Pythagoras again, and square that and square that and get the square, add them, get the square root. It gives you 6578. That's what I got. So now, but there is something about the star and the delta, which is I'll get rid of these. Remember, that was the same impedances we used for the star and the delta.
Morning.
And it kind of looked like that. It was 2 2 2 2 2090 and 754. Oh, was that 754? Yeah, that was 754 as well, full enough. Seems that bit. Now, I don't know if you can notice something about that. But what is power? Power is what? Power is current. Voltage times current, current times voltage, whatever. Now, see like in a delta, you always get a line to line voltage. So the line to line voltage means that it's magic. So what we're doing is here we're using the line voltage here, line to neutral, but in this one we're using voltage line to line. Now that is root 3 in magnitude. Anyway, it's root 3 bigger than that. So what's going to happen is, in this circuit, you're going to get root 3 times the voltage. But what's that going to do? That's going to draw the same proportion of current in. So you're going to get root 3 times the current. So what does that give you? That equals 3 times VI. In other words, because you're using line to line current, even though it's the same impedance as you're drawing in, you've got a root 3 times bigger voltage, which means you're going to have a root 3 times bigger current, which means you're going to have 3 times the power. So looking at that, 2222, multiply that by 3, and you're not far off. So that should be something like 66666. So it's pretty close. It's just my workings. And again here, 754, times that by 3, just about there, and 2090 times that by 3, that would be 6180, I think. No, 6270 in fact. So you can see there that the delta differs. It uses line to line voltage, which means it's got higher power consumption and higher current drawn in. I don't know if you've looked at induction motors, 3-phase induction motors. You start it with a star configuration because it's less power consumption, and it uses that until it gets moving and it builds up the magnetic electric fields associated with it to get it shifting. It can then handle a bigger current. That's when you change from a star to a delta. They are associated with many different applications, obviously, but so that's that. As far as the currents go, actually I'll just rub them out I'm sure you could maybe do this on your own, I suppose, because I need to get on with making more videos, and I'm going to have one more videos for yourselves looking at the capacitor across in parallel, and then I'm going to look at, I'll do one on cable ratings, just looking at overprotection, protective devices and breakers and fuses and things like that. And so that's good. Sorry, the current, remember here, I1 equals IAB minus ICA and all that. I can't remember, what were the currents? Yeah, I've got them here. So like, that would be 8.3 at minus 30, minus current CA, which is 5.33 at an angle of 140. Right, and what you do, you'll split that into its different components. So that would be cos 8.3 cos minus 30 minus, sorry, wait a second, forgetting, plus 8.3 sine minus 30 minus the 5.33 cos 140 plus 5.33 sine 140. Sorry about that. But so you split this polar into its rectangular components, and put this into its rectangular components and subtract that from them. And that's why you can, it's because of the vector addition is more complex than just normal summing and stuff. So you can get what I would imagine, you'd imagine you get a smaller current for that, whereas it depends on the angle and the magnitudes of them. Depends, you might get a much bigger current, just depending on what angle they are to each other and how the vectors add. So I don't know whether I should just do this. I'll just quickly do this one to illustrate what I mean, and then I'll let you do the rest yourselves. And this covers the tutorials that I sent you out, so I'm hoping that you can send me them back, and the single phase one, and I'll get this, draw a line under this, it'll be great. So what is that then? So it's 8.3 cos, that would be 7.2. Right, I could just do this one and add this one. Well, it doesn't matter, right? So I'll know that in case I want to confuse anybody. And 8.3 sine minus 30, that's minus 4.15 I and j. Now we're going to subtract this from it. It's 5.33 cos 140, that's minus 4.08, and 5.33 sine, yes, that's minus 3.42 j. Right, j, right, is that right? I'm just going to check that out. 5.33 cos minus 1. Yep, that's right. So what happens here then, if we just want to add these up down here, I hope you can see that. That's going to 7.2 Right. 1. That's 7.2, and it's, you're saying minus, that's plus then, so that's going to be plus 4.08, and this bit here is minus 4.15, that's minus, that's plus 3.42. So that's going to be, what's that, 11.28 minus what's that, 586873 minus 0.73 I and J. And now if we, I think that's right, I'll just make sure, don't want to make any mistakes. So that's minus 4.5 plus 3.42, so it's minus 4.15 plus yeah, 0.73, that's right. So what we're looking at then, the square root of 11.28 squared plus 0.73 squared, and that'll give you, for this one, 1.47 amps. That's going, and that was line 1, I think, wasn't it? Yeah, that was line 1. And the angle was just tan minus 1 of minus 0.73 over 11.28. That's a shallow angle. Right, so I hope that's good. Hope everything makes sense. And I'll speak to you soon, okay? Take it easy, bye. Wrote all these down here. And we just need to add them together. Remember, that's your power, that's your reactive power. So what we're looking at here, 2988, or 83 in fact that is, plus 1107 plus 2079, 6169. Oops, that's watts, and it's going to be 1722 plus 1319 minus 757. That's going to be plus, that's going to be plus 2284J. That is VARs. That's power, real power, and that's Q. Excellent. Right, so now we've got that, what we would do, I'll just flick back to the, I done it again, I had the blooming camera on and I wasn't recording. Right, so what I've done there is I've split the apparent power into its power and reactive power components, and I've just added them together to give us our final result there. And again, that's the watts, that's the VARs, your power, reactive power, and your I and your J part of that vector. I'm just going to go to the board for a second. Right, and when you add all these up, what we've got there, there's 6169, your power, and your reactive power 2284 up the side there. We just use Pythagoras again, and square that and square that and get the square, add them, get the square root. It gives you 6578. That's what I got. So now, but there is something about the star and the delta, which is I'll get rid of these. Remember, that was the same impedances we used for the star and the delta.
Morning.
And it kind of looked like that. It was 2, 2, 2, 2, 2, 0, 9, 0, and 754. No, was that 754? Yeah, that was 754 as well, full enough. Seems that bit. Now, I don't know if you can notice something about that. But what is power? Power is what? Power is current. Voltage times current, current times voltage, whatever. Now, see like in a delta, you always get a line to line voltage. So the line to line voltage means that it's magic. So what we're doing is here we're using the line voltage here, line to neutral, but in this one we're using voltage line to line. Now that is root 3 in magnitude. Anyway, it's root 3 bigger than that. So what's going to happen is, in this circuit you're going to get root 3 times the voltage. But what's that going to do? That's going to draw the same proportion of current in. So you're going to get root 3 times the current. So what does that give you? That equals 3 times VI. In other words, because you're using line to line current, even though it's the same impedance as you're drawing in, you've got a root 3 times bigger voltage, which means you're going to have a root 3 times bigger current, which means you're going to have 3 times the power. So looking at that, 2, 2, 2, 2, multiply that by 3, and you're not far off. So that should be something like 6, 6, 6, 6, 6. So it's pretty close. It's just my workings. And again here, 754, times that by 3, just about there, and 2090 times that by 3, that would be 6180, I think. No, 6270 in fact. So you can see there that the delta differs. It uses line to line voltage, which means it's got higher power consumption and higher current drawn in. I don't know if you've looked at induction motors, 3-phase induction motors. You start it with a star configuration because it's less power consumption, and it uses that until it gets moving and it builds up the magnetic electric fields associated with it to get it shifting. It can then handle a bigger current. That's when you change from a star to a delta. They are associated with many different applications, obviously, but so that's that. As far as the currents go, actually I've just rubbed them out. I'm sure you could maybe do this on your own, I suppose, because I need to get on with making more videos, and I'm going to have one more videos for yourselves looking at the capacitor across in parallel, and then I'm going to I'll do one on cable ratings, just looking at overprotection, protective devices and breakers and fuses and things like that. And so that's good. Sorry, the current, remember here, I1 equals IB minus ICA and all that. I can't remember, what were the currents? Yeah, I've got them here. So like, that would be 8.3 at minus 30 minus current CA, which is 5.33 at an angle of 140. Right, and what you do, you'll split that into its different components. So that would be cos 8.3 cos minus 30 minus, sorry, wait a second, I'm forgetting, plus 8.3 sine minus 30 minus the 5.33 cos 140 plus 5.33 sine 140. Sorry about that. But so you split this polar into its rectangular components and put this into its rectangular components and subtract that from them. And that's why you can, it's because of the vector addition is more complex than just normal summing and stuff. So you can get what I would imagine, you'd imagine you get a smaller current for that, whereas it depends on the angle and the magnitudes of them. Depends, you might get a much bigger current, just depending on what angle they are to each other and how the vectors add. So I don't know whether I should just do this. I'll just quickly do this one to illustrate what I mean, and then I'll let you do the rest yourselves. And this covers the tutorials that I sent you out, so I'm hoping that you can send me them back, and the single phase one, and I'll get this, draw a line under this, it'll be great. So what is that then? So it's 8.3 cos, that would be 7.2. Right, I could just do this one and add this one. Well, it doesn't matter, right? So I'll know that in case I want to confuse anybody. And 8.3 sine minus 30, that's minus 4.15 I and j. Now we're going to subtract this from it. It's 5.33 cos 140, that's minus 4.08, and 5.33 sine, yes, that's minus 3.42 j. Right, j. Right. Is that right? I'm just going to check that out. 5.33 cos minus 1. Yep, that's right. So what happens here then, if we just want to add these up down here, I hope you can see that. That's going to 7.2. Right. 1. That's 7.2, and it's, you're saying minus, that's plus then, so that's going to be plus 4.08, and this bit here is minus 4.15, that's minus, that's plus 3.42. So that's going to be, what's that, 11.28 minus what's that, 586873 minus 0.73 I and j. And now if we, I think that's right, I'll just make sure, don't want to make any mistakes. So that's minus 4.5 plus 3.42, so it's minus 4.15 plus Yeah, 0.73, that's right. So what we're looking at then, the square root of 11.28 squared plus 0.73 squared, and that'll give you, for this one, 1.47 amps. That's going, and that was line 1, I think, wasn't it? Yeah, that was line 1. And the angle was just tan -1 of -0.73 over 11.28. That's a shallow angle. Right, so I hope that's good. Hope everything makes sense. And I'll speak to you soon, okay? Take it easy. Bye.